大香，醒来不见爹娘面，只见床前明月。
Water may be solid, liquid, or gas, depending on the heat energy of its molecules.
Solid water is known as ice, and gaseous water is known as water vapor or steam. Ice maintains its shape. Liquid water will fill the bottom of any vessel it is placed in, and steam will fill up the whole space. While water is in liquid form, its molecules are still in motion. A drop of food coloring will gradually diffuse through the whole volume. A drop of food coloring will not do anything to the inside of an ice cube. The temperature of the water will also determine how quickly the food coloring will diffuse throughout the liquid. The greater the temperature of water, the quicker this will occur. A cycle exists that transforms water between its three phases, depending on the heat energy that is transferred. As a block of ice melts, it becomes liquid water, and as water is boiled, it becomes steam. After all the water has been converted into steam, there is nothing left inside the vessel. Conversely, boiling water may also be converted back into liquid water in the process of condensation. This is demonstrated by holding an ice tray over some boiling water. Droplets of water are formed underneath the cold ice tray. Liquid water may also be frozen by being subject to cold temperatures, such as the process of refrigeration. As ice melts, it contracts, and this is demonstrated by placing ice chips into a measuring cylinder, securing them in place, and filling the remainder with ice cool water. Over the course of the next few minutes, the water level will lower, suggesting a contraction in the volume of the ice. Because ice contracts when melting, this means that the same amount of water molecules takes up a smaller volume. Ice is therefore less dense than the water it becomes. This lesser density ensures that ice will float on the top of the water. Ice melting in a glass of water filled to the top will not overflow when it melts. Water molecules may be removed from liquid water in a process called evaporation. Water evaporates when exposed to the heat of the atmosphere. The temperature of a surface and the amount of moving air affects how long it will take to evaporate water. The surface area of the water exposed to the atmosphere determines how much is evaporated. Placing oil on the surface of the water will decrease the area affected by evaporation. 4 cylindrical glasses of water have various amounts of oil floated upon their surface. One glass serves as control and has no oil floated upon it. Another has 1 drop, a third has 20 drops, and the last was contaminated by a swish of an oily finger. Over a period of time, the level of water will diminish until eventually none is left, although this process can be slowed by placing a small amount of oil on the surface. Whereas 1 drop of oil will slow the time slightly, 20 drops of oil will be quite a bit more effective over the same time period. The experiment was discontinued as soon as oil floating on the top of the water formed clumps, and presumably some of the oil filmed a film on the sides of the glass as it lowered. When our body sweats, evaporation takes place, which requires a change in state, so energy is drawn from the surroundings and consequently it lowers the temperature. A bottle of water wrapped in a wet towel will conduct heat a lot better than a bottle of water wrapped in a dry towel, as demonstrated by cold water increasing its temperature quickly. The amount of moisture in the air also affects how easily water evaporates. An Erlenmeyer flask with a drying agent such as silica gel, and another flask holding a small amount of water in the bottom, both have thermometers with pieces of cotton wool and rubber bands tied around them. Water is more likely to evaporate if there isn't so much water already in the air. This means that the temperature in the dry flask is cooler than the temperature in the wet flask. Whilst water's evaporation lowers the temperature considerably, the use of methylated spirits in cooling evaporation decreases the temperature at a faster rate. This is demonstrated after blowing on the thermometers with cotton buds attached using rubber bands.
A block of ice weighed down in a test tube full of water will not melt even when the top of the liquid water is boiling. This experiment shows that water is a poor conductor of heat. The way that water does conduct heat is through a process of convection.
You can view convection currents by mixing sawdust with water and heating it. First, the sawdust has to be treated in order to obtain the appropriate density of sawdust by mixing sawdust with water and removing any sawdust which will not sink to the bottom of the water after mixing up and allowing sedimentation. Water that is heated becomes less dense, consequently exerts less pressure, and cooler water takes its place. To be heated, some crystals of potassium permanganate may be added to water to form a colorful deposition at the bottom, which may be limited in size by removing the glass tube whilst holding a finger over the upper end. When the crystals are heated, the color flows in patterns indicating the movement of the water within the flask. In these experiments, the sawdust or the crystal coloring rise and fall depending on how dense they are in comparison to the liquid in which they are present. A way of viewing how density affects water is using hot water and red food coloring in a small container submerged quickly in a beaker of cold water. The hot water from within the container will rise until it is floating at the top of the water. More spectacularly, a glass jar filled with hot water and some red food coloring is fastened in a vise. A glass jar of cold water with blue food coloring is placed over the top of the first jar, with a plastic partition applied in between them. When the partition is removed, the liquids mix together to form a purple color. If, however, the orientation of the hot and cold water jars are reversed, the color will remain separated for a few hours. No convection current exists in this system, and any heat transfer must take place by direct conduction. Because ice floats at the top of a jug of water, it is near the warmest part of the water, so it tends to melt quickly, cooling that warm water, thus sinking it. If the ice is held at the bottom of a jug of water with a potato masher, it only comes in contact with some of the coolest water. Ice will cool water quicker if it is at the top of the jug, because cooler water is denser and consequently sinks lower. Ice at the bottom of the water does not have the scope for convection that ice at the top has. It takes a lot longer to melt. Boiling water goes through phases of liberating the gases inside, such as air, then creating bubbles of steam, which are reabsorbed higher in the liquid. Soon the bubbles are big enough to escape the liquid and burst upon hitting the surface. Water may be boiled in some paper, providing that paper readily gives off its heat energy to the water. It is possible to set up experiment to recapture the steam. When water is boiled, the steam contains water vapor and the other gases, which escape with the vapor. Water condenses in the condenser and may dissolve the gases. Tap water contains many impurities that affect its properties, and so distilling is a process to remove these impurities and purify the water. Solids remain behind in the boiling vessel. The resultant liquid is still satisfactory for laboratory purposes and is known as distilled water. A Liebig or spiral condenser are used for condensing liquid. Making a solution with a lot of impurities, salt, and boiling it, the temperature at which it boils is increased.